Imagine a world without electricity. No lights, no phones, no internet. Sounds impossible, right? But do you know how electricity actually works? It's not magic, although it seems like it sometimes. Electricity makes our modern world go round. Let's break it down in the simplest way possible. What is electricity anyway? You can't see it, but you can sure tell when it's there. Well, electricity is simply the flow of electric charge. You know how water flows in a river, right? Well, charges, those teeny tiny particles, move through a conductor like a wire, just like that river. This movement of charge is what we call electric current. Think of it like this. Imagine a bunch of excited electrons, those tiny particles inside atoms, all eager to move. They zoom through a wire, creating a flow of charge. The more excited electrons, the stronger the current. Now this flow of charge, this electric current, is what powers our world. From the light bulb illuminating this room to the phone in your hand, it's all thanks to the the science of electricity. What is the SI unit of electric current? Ampere A. Okay, so we've got our electric current, our river of charges flowing through a wire. But for this current to do anything useful, it needs a complete and unbroken path. That's where circuits come in. Think of a circuit like a racetrack for our charged electrons. It's a closed loop where the electric current can zoom around without any roadblocks. A battery acts like the starting line, giving those electrons a push to get them moving. And just like a racetrack needs a starting gate, our electric circuit needs a switch. A switch controls the flow of current. Flip it on and it's like opening the starting gate, the circuit is complete and the current flows, powering our devices. Flip the switch off and it's like closing the gate, the flow stops. 1 ampere means a whole lot of charge is flowing through that wire every second. To be precise, it's 6.24 times 10 to the power of 18 electrons. Write that down, it'll be on the test. Unit of charge equals sign Coulomb, C. How many electrons make up 1 Coulomb of charge? 6 times 10 to the power of 18 electrons. Okay, so we know electric current is the flow of charge, but what makes these charges move in the first place? What's the driving force? That, my friends, is all about electric potential and potential difference, also known as voltage. Imagine a water tank perched high up. The water in that tank has potential energy due to its height. It's just itching to flow down. Similarly, electric potential is like the electrical height. It's the potential energy a charge has due to its position in an electric field. Now, if you connect 2 tanks at different heights with a pipe, guess what happens? You got it, water flows from the higher tank to the lower one. The same principle applies to electric charges. They flow from a point of higher potential to a point of lower potential. This difference in electrical height is what we call potential difference or voltage. And just like we measure the height difference between those water tanks, we measure potential difference in volts, V. The bigger the voltage, the greater the push on those charges, and the greater the flow of current. Think of it like a steeper hill. The bigger the height difference, the faster that ball rolls down. A battery, our trusty source of electrical energy, provides this potential difference. Which instrument is used to measure potential difference? Voltmeter. Chapter 4. Ohm's Law, the Golden Rule. Alright, science fans, it's time to talk about the golden rule of electricity. The one that connects voltage, current, and resistance. Ohm's Law. This law, discovered by the brilliant Georg Ohm, describes the relationship between these 3 crucial electrical concepts. Ohm found that the voltage across a conductor, that's the potential difference, is directly proportional to the current flowing through it. In simpler words, if you increase the voltage, the current increases too, as long as the resistance stays the same. Think of it like this. Imagine you're using a hose to water your garden. The water pressure from the tap is like voltage. The higher the pressure, the more water flows through the hose. The amount of water flowing through is like the current. Now what about resistance? Well, resistance is like the width of the hose. A narrower hose resists the water flow more, so less water gets through, even if the pressure is high. Similarly, in an electrical circuit, resistance, R, is the opposition to the flow of current, and it's measured in ohms, Ohm. Ohm's law neatly ties these concepts together with a simple formula, V equals sign IR, where V is voltage, I is current, and R is resistance. Now here's a quick question. If resistance increases, what happens to current? The answer is, current decreases. Chapter 5. Resistance and factors affecting it. We've talked about resistance, but what exactly is it and what affects it? Well, think of resistance as the roadblocks our eager electrons encounter as they zoom through a wire. Several factors influence this electrical friction. One is the length of the wire. The longer the wire, the more resistance it offers. Imagine running a marathon versus a sprint. The longer the distance, the more tired you get, right? The same goes for electrons. The longer the wire, the more resistance they face. The thickness of the wire also plays a role. Thicker wires have less resistance, just like a wider road allows for smoother traffic flow. A thinner wire is like a narrow road. It creates more resistance, making it harder for those electrons to zip along. The material of the wire itself is another crucial factor. Different materials have different levels of electrical conductivity. Copper, for instance, is an excellent conductor. It has low resistance, so electrons flow through it easily. Chapter 6. Now let's talk about how resistors, those components designed to resist the flow of current, are connected in circuits. There are two main ways to connect resistors, in series and in parallel. Imagine a series circuit like a one-lane road. All the cars or electrons have to follow the same path, one after another. In a series circuit, the resistors are connected end to end, so the current flows through each resistor in a single path. The total resistance in a series circuit, you simply add up the individual resistances, R1 plus R2 plus R3 and so on. It's like adding up the length of each section of that one-lane road. Now imagine a parallel circuit like a multi-lane highway. Cars have multiple paths to choose from, so the traffic flows more easily. In a parallel circuit, the resistors are connected side by side, creating multiple paths for the current to flow. Which circuit type is used in homes, series or parallel? Parallel! So that if one device stops working, others keep running. Chapter 7. Ever wondered why electrical appliances get hot? That's Joule's law of heating in action. When electric current flows through a resistor, some of the electrical energy gets converted into heat energy. This happens because the moving electrons collide with the atoms of the resistor, making them vibrate faster. And what's faster vibration? Heat. Joule's law quantifies this heat generation. It states that the heat produced in a resistor is directly proportional to the square of the current, the resistance, and the time for which the current flows. The formula, H equals I squared RT, where H is the heat produced, I is the current, R is the resistance, and T is the time. Chapter 8. Let's wrap up our electrical adventure with a look at electric power and energy. Power, in general, is the rate at which work is done, and electrical power is no different. It's the rate at which electrical energy is used or transferred in a circuit. We measure electrical power in watts, named after the ingenious James Watt. 1 watt is equal to 1 joule of energy used per second. And here's a handy formula to calculate power. P equals V1, where P is power, V is voltage, and I is current. That means the power consumed by an electrical device is the product of the voltage across it and the current flowing through it. But there are other ways to express power. We can also use Ohm's law to rewrite the power formula. Since V equals IR, we can substitute IR for V in the power formula, giving us P equals I squared R. So many formulas, so much power. So there you have it, the electrifying world of electricity. From the flow of charges to the power of circuits, we've covered it all. Remember, electricity powers our world, but understanding it is just as important. Stay curious, keep exploring, and ace your Class 10 boards. Which topic in electricity do you find most challenging? Comment below.